Good evening, good morning, good afternoon. What I'm doing right now is a recording, I suppose, of what was covered today in class, October 5th, and what will be covered in October 6th. It's the same thing. Um, so without further ado, let's get started here. Let's share the screen, share our computer sound, and we'll get started here. Okay, so first things first, you might have noticed our Schoology has changed. All of those weeks, all of those different assignments have been now organized into just one single folder, Unit 1, Measuring Matter and Energy, because that's what we're doing here in Unit 1, Measuring Matter and Energy. So you'll see weeks 1 through 7 all organized in there, and when we're done with week 8, that will be put in there as well. Last week, we finished off our quiz, and so if you'd open the week 7 materials, you'll find access to our quiz here. Today, let's take a look at the agenda and get that sorted out. This week, we have 10-week grades due 8 a.m. Friday. So teachers have to turn in grades to counselors and admin at 8 a.m. Friday. So on my end, I'm going to be finalizing grades for the 10-week at Wednesday night. Take that for however you will. This Thursday, I'll be posting up a new version of that quiz in accordance with mastery, right? I'm gonna let you guys take as many times as you need to prove mastery until we're done with the unit at least. But you'll have to take this quiz on your own time, and that's even if you want to. A lot of you guys were able to finish the quiz on time and with what I would say are adequate scores. And so if you choose not to take the quiz, that's perfectly acceptable. Finally, remember that if you do tell me something like, "Oh, Mr. Azad, I turned in the syllabus. Why did I get a 0 for it?" Um, Remind me. That's fine. Remind me, and I'll post up the update for that. So that. So the plan for today, we're going to review the quiz, each and every single one of those questions. We're going to transition over to notes, physical and chemical changes. And then on Wednesday, we'll do the same thing, right? Continue off with those notes and start on our second to last assignment for this unit. This Friday is a even professional development day, meaning you get out early at 12:40 and you take your even classes. On my end, what that means is that on Friday, I'll be doing office hours from 12:40 to 1:15. Okay, so what are we doing? Couple updates about your quiz. Let me make sure we all have that. We're on the same page here. Couple updates about your quiz. Let's go to these settings. You should all have 3 attempts at your quiz. 2 attempts seemed a bit inadequate because many of you guys were having trouble. Internet access just shut you down, whatever. So 3 attempts on this version of the quiz. And the second version might just be 5. I honestly don't see you guys doing more than that many attempts. So I grade by the highest score. And for the most part, the results were pretty decent. Let me go by question here. Pretty decent results. So that was good to see. Um, Again, more into detail when we get started here. So on your Schoology, you'll find something called Unit 1 Quiz Review. Go ahead and click that. The instructions say to copy and paste our quiz review into your evidence notebook. So you go ahead and click the link. You'll find access to this thing. Highlight all of it, copy it over to our evidence notebook. I'm zoomed in here. I'll zoom it back out. So right after the notes on scientific notation, you should have space left over and then just Unit 1 quiz review. That's what you're going to do. Copy and paste it, and we'll get started here. So on my end, this quiz is organized in 10 questions, and this was the order these questions were in. On your end, these questions were randomized, and you got them whenever you got them. So the first question is to order these units from smallest to largest. So we had, in no specific order, nanogram, kilogram, milligram, microgram, centigram, and megagram. No real order to that. The key to this question was found in notes using units of energy. It is this chart right here. Let me zoom in a bit, 150%. It is this chart right here. This chart goes from largest to smallest. I'm asking you to basically reverse the thing. So just at the bottom here, from smallest to largest, we have nanograms, followed by micrograms, followed by milligrams, followed by centigrams, followed by kilograms, and last but not least, those megagrams. That's it. You just have to put them in that order. A few of you guys mistakes was to reverse that, do largest to smallest, and that was just a very straightforward mistake. Use your second or third attempt to fix that up. Number 2, a student measures the mass of a substance as 1.7132 kilograms and its volume as 0.65 liters. What is the density of the substance in kilogram per liter? Round your answer to the nearest significant figure. So 2 steps to this question. Density, you have to be able to find density, and that's given in this formula. The first formula in assignment 3, and that is mass over volume. But the most obvious way, that's just obvious. The less direct way, the more subtle way that I would try to mess you up on this question is the significant figures. So let's talk about that. Our 2 numbers. Let's go ahead and... So density is equal to mass over volume. And our 2 numbers are 1.7132 and 0.65. As far as significant figures go, that's what you need to start with first. Find out how many significant figures each of these numbers have. So we have 1.7132 and 0.65. For 1.7132, those are all non-zero numbers, meaning these are all significant. So we have 5 significant figures. For 0.65, that 0 at the front does not matter. It is a leading 0. It doesn't count. So we got 2 significant figures. That means our final answer for density has to be reported with 2 significant figures. So let's carry this equation out. Our mass is 1.7132 kilograms divided by 0.65 liters. And so we're going to get a number. Let's figure this out. 1.7132 divided by 0.65. And so we should get 2.6356. Of course, this is way too many significant figures. We have to reduce our number. We have to round it off until it is 2 significant figures. That is 2.6 kilograms per liter. Okay, so we've rounded off our answer to 2 significant figures. And on your answer sheet, you would have been given the choice of like 2.6356, 2.635, 2.63, 2.6, and 2. I think I rounded off to 3. So you would have been given multiple options, and you had to pick the correct one. For number 3, this question on your test was a matching question. You had to match the percent error to the experimental value, which means that you should have been calculating percent errors for each of them. This is fairly straightforward, and we're just going to go through this. A student measures the density of an object 4 times. Gets 4 different results. The actual density is 1.17. So match the experimental values with the correct percent error, and I'm giving you the equation for the percent error. So if we recall correctly, the experimental value is the number you get from the experiment. The actual value is the actual value that you're looking for. If in this case, we're looking at the density of an object, and we know the actual density is 1.17. And when we try to find it ourselves, we get various answers. And so we just plug in. So for experimental value, we plug in 1.05. We plug in 1.12, 1.31, 1.24. For actual value, we know the actual value of the density is 1.17. So instead of actual values, 1.17, 1.17, etc., etc., etc. Times it by 100, and now we just fulfill this calculation. 1.05 minus 1.17, about negative 0.12, but there's an absolute value, so 0.12. Divided by 1.17, and we get a percentage of 10.25%. Right? Do it again. 1.112 minus 1.7, that is 0.05 divided by 1.17, 4.27%. So on and so forth, right? 0.31 minus 0.17, 0.14 divided by 1.17, 11.96%. 0.07 divided by 1.17, 5.98%. And so you just have to match the correct percent error to the experimental value. You see here that the most accurate number was 0.112, followed by 0.24, even though they're in completely different directions. But they're close enough to the actual value of 1.17 where the percent error is very good. Okay, next up, a beaker contains 0.250 liters of a liquid, and a student pours out 0.00385 liters of said liquid out of the beaker. How much liquid remains? Use the correct amount of significant figures to answer your question, to report your answer. Again, very straightforward, you're doing subtraction. What is not straightforward is the significant figure, so let's start with that. 0.250 liters. How many significant figures is that? That is three significant figures. The 0 at the front doesn't count because it's a leading 0, but the 0 at the end does count because this number does have a decimal, and it is after a bunch of non-zeros. It's after 2 and is after 5. So 3 significant figures here. 0.00385. That's got also 3 significant figures. Those zeros at the beginning don't count because there's no non-zero in front of them. If, for whatever reason, I had 10, right, 10.0385, then all of those numbers will count. But because I don't, it doesn't count. So our final answer is going to be reported with 3 significant figures. So let's do this. 0.250 minus 0.00385. That's going to equal 5. Messed up. 0, 5. There you go. Going to equal 0.24615. That is 5 significant figures in our answer. Significant figures, my bad. And so we're going to reduce this off to 3. So our final answer is 246. 3 significant figures. And so again, you would have been given multiple options: 246 and 1, 246 and 15, right? 0.24, 0.246. So you would have been given multiple options, and you had to select the correct one. Number 5, we have what happens when you hold a cold drink in your hand. Now, remember, cold as a concept related to energy doesn't exist. There is no such thing as cold energy. It's all thermal, right? It's either you have heat or you don't. And so, in this case, if you have a cold drink in your hand, what happens is it's not that your hand is getting cold, it's just that the heat is leaving your hand in order to warm up the drink, right? It's the same thing with a cup of coffee. The heat from the coffee leaves the coffee in order to warm up your hand. Heat wants to balance it out, wants to balance itself out. So if there's an area of low heat, it's going to want to try to rise up so it matches the rest of the area, right? If you have a desert and, like, I don't know, a tundra right next to each other, those temperatures will want to balance each other out, right? They'll eventually find a nice middle ground. And so the heat from one area will enter the other area in order to balance it out. And so when you have a cold drink in your hand, the temperature of the drink does increase. Energy is transferred from your drink, from your hand to the drink. Let's look at these other options. The temperature of the drink increases, that is correct, but energy is not transferred from the drink to your hand, right? What is cold? It's just when your particles don't have a lot of energy, right? If they got a lot of energy, they start to warm up, they move faster, and you take up a little bit more volume. The temperature of your hand increases. Well, we know that's just not true. If you have a cold drink in your hand does not suddenly increase in temperature. The temperature of your hand decreases, okay? Energy is transferred from the drink to your hand. What energy is in the drink? There is no energy in the drink. It's very low energy. That's why it's cold. And so our remaining choice has to be C. Let's take that kind of process of elimination and do it and apply it to number 6. Which statement describes what happens inside of a liquid thermometer that shows an increase of temperature? The volume of the liquid decreases because of an increase in kinetic energy. Well, let's think about this first. Inside of a liquid thermometer that is showing an increase in temperature. So what happens to a thermometer when it's increasing in temperature? That little red line goes up, okay? And so the volume of a liquid decreases. That's just not true because that liquid, the red line, is increasing. So that immediately knocks out this one. And we're good there. Well, the movement of the particles decrease because of a decrease in kinetic energy. So the temperature has increased, therefore the kinetic energy has decreased. That's not right. If temperature increases, right, that's thermal energy. That's thermal energy that's increasing. And so that's not true. You can't have a decrease if your temperature is increasing. That's just not how it works. The volume of a liquid increases because the movement of those particles decrease. So let's take a step back. An increase in temperature. You increase the energy of the system, right? Those particles are increasing in temperature. So are they going to move slower now? Is something that is highly energized going to move slow? It's not correct. So our final answer is the only one that's remaining. Choice D. For number 7, we just got to match the type of energy to whether or not it's kinetic or potential. To just quickly go through that, refer back to number 1 in describing changes of energy. We have all of our different types of energy organized as either potential or kinetic. So I'm just going to straight up copy that and paste that to here. Now, for number 8 was the question that I had, I would say, the most disappointment with. We're describing the energy changes here. I've had multiple students type in chemical changes, which is not incorrect, right? If you burn a marshmallow over a fire, you, of course, create a chemical change. However, in this question, I am asking about the energy change. And so, to signify my disappointment, I just want to point out this thing right here. It is very obvious sometimes when a student is, how you say, pulling a fast one. Let's call it that. If you posted this question word for word, I know what Quizlet is. I know how to Google answers to questions. That is not what I'm looking for in a quiz. And if you happen to turn this one in, you might notice that your quiz was a 0 instead of anything else. So, describing energy changes that occur when a marshmallow is burned over fire. If you straight up put a marshmallow burns, it undergoes color changes and it caramelizes, fine, that's cool. It doesn't answer the question, and I will see you later as you take other quizzes. So, Quizlet is a thing. I know how Google works. I'm talking about energy changes here. And so, with a marshmallow, what is a marshmallow? It's a piece of food, right? Marshmallows are food, right? That is stored. Marshmallows are potential, right? They're potential energy. It's just chemical. right? It's chemical energy stored in the food. You eat it or you burn it. So when they're burned, and this is the phrase here, energy is transformed, right? You turn the marshmallow from chemical energy, from potential energy, into kinetic energy in the form of thermal, right? Into heat. And so that's what you should do. If you mentioned thermal energy and chemical energy, you got the point. If you mentioned energy being transformed from potential to kinetic, you got the point. I'm not talking about chemical changes in this question, just be aware of that. All right, for number 9, students are attempting to find density of an object. They find the results are neither accurate nor precise. Explain how several factors can cause these errors in accuracy and precision. I was actually very satisfied with your responses overall to this question. Most of you guys referred to human error, right? Either they miscalculated, right? They didn't measure correctly. They used the wrong equations, right? Those are all human errors. A few of you guys went further. And hold on. Talked about density problems, right? It was too hot, so heat made objects lighter. So great use of any kind of knowledge you've already bring to the table. Think about most metal, right? If you heat up a metal long enough, it'll become a gas, which is less dense. So you take that concept and you apply it to most things, and you'll see that heat will typically change the density of an object, right? Lighter or heavier, depends on what kind of object you're looking at. You take ice and you heat it up, it becomes water, which is, heavier than ice. For number 10, I was very satisfied. It was just a progression of satisfaction here. For number 10, I was very satisfied with your lot's reasoning as far as the Casino conversion goes. We're taking value on a food label into grams in order to count the servings, right? And so you have 1.5 pounds of food. So let's go ahead and write this out, our plan. We got pounds. We want to turn them into grams. And we want to turn our grams into servings because our final question is how many servings of food are in this package. So pounds to servings to pounds to grams to servings. Your reasoning was very well done. 1.5 pounds of food. I know 1 pound is 453 grams, so 1.5, that's like 453 plus like half of that. 453 plus half is like 220, so maybe 670 or so grams of food. 100 grams in a serving, I've got 670 grams, so I've got 6.7 servings. A lot of you guys did that reasoning, and I really enjoyed seeing that. That was well done, in my opinion. A few of you guys proved yourselves in the math, and let's just go ahead and do that. 1.5 pounds. Our plan is to turn pounds into grams, so pounds times grams, 453 grams, times 1 serving, going to equal something. Well, we know it equals about 6.7 grams, but we're going to wait for that. Our starting material is pounds. We can just leave the denominator blank for that. But 453 grams is equal to 1 pound. We're going to put that underneath. This is basically a fraction, by the way. 1 serving is equal to 100 grams of the stuff. And so we have pounds over pounds. They cancel out. Grams over grams, they cancel out. Our final answer is in servings. And it's about 6.78 servings. Right? 1.5 times 453 times 1. It's about 678 or so divided by 100, 6.78, and you're done. That was very well done, in my opinion. Good job, you guys. And with that, we are done with the quiz review. Next quiz will be opened up on Thursday. Take it on your own time if you want. I will not force anyone to take a new quiz. It is just sometimes in your best interest. This quiz will be up until we finish the unit. At that point, we are moving on. So if you do not take the quiz at that point, tough cookies. All right. So according to the agenda, we are now moving on to notes, physical and chemical change. Let me go ahead and publish this on all of our ends here. That same deal like before. You're going to want to go ahead and click on that, copy and paste it into our evidence notebook. So we're just going to go ahead and do this. Copy and paste it. And you see here, our table of contents is becoming ever more massive. We finished the Unit 1 quiz review, and now we're on notes, physical and chemical change. Now, I'm referring back to the slideshow, so just have that, be aware of that. Notes week 4, don't ignore that for now. We're just going to call this a notes slideshow. So we're starting with identifying physical and chemical properties of matter. I'm going to stop very soon because we're going to finish this off next time on the Wednesday, Thursday video. But for now, let's just finish off the first half here. We are talking about physical and chemical changes. And so what is matter? What is matter? Provide an example of matter. Basically fill in the vocab. So matter is everything. Everything is matter. Matter is the building block of all substances that we currently know of. If it's not matter, it's antimatter, which by definition is the opposite of matter. And so if you define yourself in relation to something else, that thing is the key thing. Matter is the key thing. And so to provide an example of matter, literally, you can name any object and it is an example of matter. So I'm just going to move right past that. Take a look here. What is matter? It's anything that takes up space and has mass. And so if we're looking with this video here, let's take a look here. We have a ball of clay. The mass and matter in this images. Is it changing? Look at the big ball. Big ball is not changing. Look at the pancake ball. The mass is the same. The amount of matter in that object is still the same. If you look at those little tiny balls, right, it's the same amount of clay. It's the same amount of matter. It's just split up into different places now. So the mass might have changed, but overall it hasn't, really. That mass is still the same. If I took up all those balls and weighed them, they still have the same amount of mass. The matter is still the same. I've not increased or made new matter, so we're good. And so that is an example of physical properties, right? The amount of mass in an object, the amount of space it takes up, is a physical property. And so a physical property is a property that can be measured or observed without changing the identity of the matter. That comes into play when we start talking about chemical reactions. And so let's give a few examples. What are some examples of density, conductivity, magnetism, solubility? What do these properties have in common? Let's take a reverse aspect here. These properties are all physical properties. These are all physical properties. And so anything we could think of, if it relates to density, that's a physical property. If I have a block of gold and a block of aluminum, gold is more dense than aluminum, right? So let's just write that down. Gold is more dense than aluminum. Conductivity, how well something conducts electricity, right? And so let's take another example. Sand is worse at conductivity than copper, right? It's fine to stick sand up an electrical socket. I mean, it will mess up the socket because you can't plug anything into it, but don't put a copper fork in there to conduct electricity directly to your heart. That's not a good thing. Magnetism. right? Plastic, not magnet, not electromagnetic at all. Copper, super electromagnet, right? Super magnetic, right? Metals are magnetic. Non-metals are not. These are examples. Solubility, that's just how well something dissolves in water. So if I took some copper and I threw it into the water, it wouldn't really dissolve. It would actually react. And that would be a chemical change because the copper would rust. Solubility, though, table salt, right? Table salt in water would dissolve. And it doesn't change the properties of table salt. I could get that table salt out of the water pretty readily, right? Take some electricity to it, separate out the salt in the water, and boom, I am set. I have my table salt back. Those are just examples. Finally, what is a physical property? We're just going to write down that definition. It's a property that can be measured or observed without changing the identity of the water, of the matter. So if I have a paper, right, I rip it up, right, I still have paper. This has not changed. However, if I were to burn said paper, I can't get it back. If I burn this paper, I am done. The paper is gone. It has changed identity. It is in the wind. I'm not going to burn the paper on screen. We're going to pause it there. Actually, no, my bad. We're going to finish off two more, and we'll call it a day. What is the law of conservation of matter? It's a very similar law to energy. It cannot be created or destroyed. You cannot create matter, and you cannot destroy it either. Yep. Yeah. You cannot create or destroy matter. Very similar to energy. There are states of matter. There are 5 of them. 2 of them are a bit extreme, but you know the other 3. Solid, liquid, gas. Solid, liquid, gas. And you guys know the 4th, sometimes, plasma. And so it kind of goes like this. You have a solid. Let's take ice. You have a solid, and you add heat, it turns into a liquid. You take liquid, add heat, it turns into a gas. You take a gas, add heat and pressure, it turns into plasma, right? Basically, purely energetic stream of particles that is like a clump. Highly energetic, highly damaging to most things, and most of the universe is plasma. We could go the opposite direction. I say there are 5. If you go the opposite direction and cool things down, right? Plasma cools into gas, gas cools into liquids, liquids cool into solids. And so we could go even further, cool solids even more. We get something called a Bose-Einstein condensate. Like a condensation, right? You take a liquid and it condensates on the side of your cup. A condensate is just a really cool object. It doesn't do anything. It is so cool. Those particles have basically collapsed into each other, and you basically have a super solid chunk of cold object. So that's a very nice, very cool thing that didn't really exist until like 1995 when we finally were able to reproduce it in a lab. That's some cool stuff. Real cool stuff. Anyway, this video is going to go on a bit too long. This is the October 5th class recording. Basically, if you missed out on today's lesson, it'll be up on the YouTube, and I intend to be doing more of these in the future. So I will see you all later. Hope you have a great time. Make sure you fill out those quiz reviews and quizzes and get your assignments in, and I'll see you all later. Bye-bye.